So I'd like to use the Fermionic path integral to derive the Feynman propagator. And as I was doing this, I noticed that in Weinberg's marvelous volume 1, he never writes down an explicit formula for the Feynman propagator, for fermions. And so it was hard to check that what I was doing, to see whether what I was doing was right or not, but I think it was. All right, so let me show you. Let's first of all go back to an identity that's related to Gaussian fermionic path integrals. It's equation 16207, and it looks like this. Integral theta dagger a theta plus theta dagger zeta plus zeta dagger theta d theta star d theta is, and I'm going to write two equations for this. E to the minus theta dagger a theta plus zeta dagger a inverse zeta, and then d theta star d theta. And of course you can rewrite this as a determinant, so you can rewrite this as a determinant of a times e to the zeta dagger a inverse zeta. Okay. And so when I derived that last week, you might have thought that he's gilding the lily. I told you about the dentist, right? You had a patient in Lily. Yeah. Okay. Anyway, what I had in mind was that you can actually do something quite useful. Now, this is written in terms of dagger, but of course, anything dagger, like psi dagger, you can define psi bar, and that's I psi dagger gamma 0. And again, since I'm following the notes of my book, I'm using Weinberg's notation, so the gammas differ by I. You can then write this in the following way: e to the minus theta bar a theta plus theta bar zeta plus zeta bar theta d theta bar d theta is e to the minus theta bar a theta plus zeta bar a inverse zeta d theta star d theta, or d theta bar d theta, I guess. Anyway, so this is the relation I want to use, and apply it to a one of these z's, and I'm going to change my definition of z slightly. I'm going to have z0 z0 of zeta, vacuum time-ordered product e to the integral zeta bar psi plus psi bar zeta e4th x. And because this is all time-ordered and so forth, what that means is that these things depend upon time, therefore there are time evolution operators, and so this thing is actually an integral e integral zeta bar psi plus psi bar zeta plus I, the fermionic action, which is, we can say, L0 of psi. I'll put in an epsilon and then d4th x. And the epsilon I'm not going to go through the epsilon routine, but it comes from the matrix elements of the Grassmann coherent state with our ground state, or bare ground state. And then in the denominator we have e to the integral I L0 sine epsilon equal of x. And okay, so this is a definition. This, as I said, is basically a mathematical. These z's are always mathematical devices to compute other things, and in this particular case, well, we first of all have to figure out what A inverse is. And the A inverse will be the inverse of the differential operator in here. Or actually, it's the differential operator in here is the inverse of something else. It's an easier way of thinking about it. That L0 is, let me just write that down. L0, or rather IL0 is what occurs there. IL0 is minus I gamma, well, it's, well, I wrote it in terms, I switched from chi to psi here. So if we stay with psi, then it's, an eraser, it's not wet. So this would be okay. I don't know why I switched from chi to psi. There was probably some interference in the neurons there. Anyway, this is our this is the fermionic action, and so what'll this tell us? In other words, what we've got here is well, before we go to that, let me give you this identity involving this differential operator, namely I gamma mu d mu, which we could say is, you know, p slash plus m on this delta of x minus y, and let me now define what delta is. This will be I gamma mu d mu plus m, and this delta is going to be an integral d4 p pi to the fourth e to the I p x minus y, and then minus I times, actually, let me put the minus I out in front. I think that would make things a little bit clearer. And then this is minus I gamma nu d nu, no, gamma nu p nu plus m divided by p squared plus m squared. Okay, so the delta, big delta, is this thing here. Now, when this acts, of course, the I cancels the minus I. The d mu brings down an I p mu, and so this thing is an integral d4 p 2 pi to the fourth, and now, of course, e to the I p x minus y. The derivative is with respect to x rather than y. And so what we have then here is I gamma mu p mu plus m minus I gamma nu p nu plus m p squared plus m squared minus I epsilon. And now this is just this thing that we, you know, learned in high school: x minus y times x plus y, x squared minus y squared. In this case, it turns into p squared plus m squared. Of course, what we're using here is the fact that the gamma nu is 2 eta mu nu. And so what we have here then is p slash is just p squared. And so what we get here is p squared plus m squared cancels, and this then is integral d4th p 2 pi to the 4th e to the I p x minus y, and then this is just delta 4 of x minus y. Well, what that tells you then is that this thing is the inverse of that. And we're thinking of this as, of this differential operator and this structure here as being a matrix in 4-dimensional space. And so that's how that works. Now, any questions? Okay, so let's go to the next step here. What we can say then is that we've got a differential operator here, I gamma mu d mu plus m, and the inverse of that is this big delta. And so this structure here is in fact of the form e to the minus psi bar a psi, where a is equal to I, it's I gamma mu d mu plus m. So this is the matrix A, and the structure there then is minus psi bar a psi. And so we can rewrite it as, in other words, we get the following relation. We get the time-ordered product then will be to the integral zeta bar psi. Well, that's why I switched to psi. That's what I wrote in these notes. What do you know? Okay, psi bar zeta d4 of x is then, and of course this is this ratio of integrals and now what we have is minus I that divided by and of course this is d psi bar d psi. Okay, so this is what we start out with. And now using this identity, we can rewrite this as e to the integral. And what does this give us? This says that if you have a minus here, you then get this plus zeta bar A inverse. So this should be something like zeta bar A inverse zeta d4 of x. And then, of course, what you have is what's left. Maybe I should do this in 2 steps. So this is sort of in a thought cloud. This thing turns into an integral e to the integral zeta bar A inverse. Well, the A inverse is just delta, isn't it? So this is, in other words, zeta of x, delta x minus y, zeta y, but now it's d fourth x, d fourth y. And then we still have this part, and the analog of that, of course, is there's this action here. And so we have minus I integral psi bar gamma mu du plus m psi d fourth x, and now this is d psi bar d psi, and underneath we've got just this, and so this is E, let me just write it I as 0 d psi bar d psi. Well, there's no psi and psi bar in here. This is exactly the same as that, and so all of that stuff cancels. The big path integrals cancel, and we're just left with E to the integral zeta bar of x, delta x minus y, zeta y, d fourth x, d fourth y. So this time-ordered product with these Grassmann currents is then just a simple exponential of Grassmann currents. These zetas are playing the role of J in the bosonic case. And so let me sort of separate those things out there. All right.
So no determinants. No determinants.
No. We don't need the determinant because the functional integrals cancel. So the integral d psi bar d psi of the e to the I as 0, the numerator and the denominator cancel.
Okay.
As they did in the bosonic case.
Okay.
Here.
Thank you.
Any other people have asked questions that didn't get candy? Is anybody particularly hungry?
Not yet.
The lecture doesn't last that long. All right, well, what we can do now is we can differentiate functionally with respect to zeta bar and zeta. And notice what we do is we differentiate functionally from the left with respect to zeta bar and from the right with respect to zeta. And so what we find then is, and then we set, of course, zeta equals 0. In doing that, what we get is time-ordered product psi of x, psi bar of y in the vacuum is, well, it's this delta, nothing more than delta. And delta, of course, is minus I integral d fourth p 2 pi to the 4th e to the I p x minus y minus I, if you want, minus I p slash plus m over p squared plus m squared minus I epsilon. Okay, so that's the Feynman propagator. And so you see these functional integral relations are, I mean, there's a certain amount of magic there, but this gives us the Feynman propagator for fermions in a way that's much easier than the way in which you get it in a standard course. And in fact, I was able to find somewhere in my notes a derivation of a standard derivation of that, and it involves one of these spin sums, and you remember the spin sums were something of a nightmare, so in fact then when I wanted to check what I was doing to see, because it was Schrednicke uses Weinberg's metric, but he uses a different set of gamma matrices, and other conventions are different. And Weinberg never writes down that equation at the bottom of the board. And it's that, I mean, he derives everything, and he doesn't need to write that down, but that, you know, leaves mere mortals like me somewhat unsettled. Okay, so any questions? Yeah.
Yeah, the second line, second equation there, Newton there is some integral of exponential a minus b.
Where are we? Where are we?
No, I mean, this is something integral exponential a minus b, and this is integral e to b.
Right.
So how can you cancel that? And those are
Well,
Grassmann.
Well, this thing, e to this Grassmann expression integrated, that is simply a Grassmann number.
Okay.
So you factor it out, and what you have left is integral e to the minus I, all this stuff, d psi bar d psi, and that's exactly the same as the denominator.
Can you just simply move the first part out?
Yeah, of course.
It's not so straightforward for me.
I mean, in other words, this thing here. All right, let's do it this way. Let's make that a number and write this as
can we
e
do
to the
that? Can we
minus
do
I.
this?
Well, it's the product of two exponentials is the exponential to
No,
sum.
they are
right?
Grassmannian variables. They are Grassmannian.
What?
They are
Grassmannian.
Grassmannian.
So
So
what?
it works.
Yeah, yeah.
Okay. That's my question. Okay.
Okay.
You
So
know,
this
we
is
have
just
a-
a number.
we
We
have
factor it
operators
out,
that
then the remaining functional integrals cancel.
He might be referring to when you have operators that don't commute and you want to do something like e to the a times e to the b is e to the a plus b plus the commutator times a half plus
Well,
b
but
squared.
this is quadratic in Grassmann, so it's it commutes.
Yeah, so
with
it's just a
everything.
real number
Yeah. Well,
or something of that.
it's not real. I mean, it's very least complex, but no, it's really Grassmannian because you do a power series in that exponential pretty soon you get 0. Okay, so let's now go to back to the world of bosons and talk about non-abelian gauge theory. We were talking about that last time, and what we saw is a generic non-abelian gauge theory is minus a quarter Fa mu nu Fa mu nu minus psi bar gamma mu d mu plus m psi, all at d forth x. And so what are these things? Well, first of all, Fa mu nu is d mu A nu minus d nu A mu, and then G, structure constants of the group, AB mu is C nu. So, very nice expression, and there are nice ways of writing this, but I haven't rehearsed them lately, so I will try to do them. And this thing, of course, is the easy way to understand this algebra is to say that this is d mu plus a mu psi, and identify it as the matrix a mu minus ig ta aa sum. And then you can see that this is, that you have invariance under the local transformations Hell, I didn't do this. Well, maybe I'll have to, maybe it's worthwhile doing this again. What we want is if psi prime of x is u of x, psi of x, then we want d mu psi prime to be u of x d mu psi, well, of x, of course. And so that means that we want d mu plus a prime mu on u of x psi, and I'm going to leave out the psi, is u, in fact I'm going to leave out the x also, is u d mu plus a mu. So this is what you need, and this tells us that a mu prime u is u a mu plus u, no, just u a mu. Wait a minute, I need a d mu somewhere. It was a d mu u here. So d mu u, the left-hand side of that is d mu u plus a prime u is u a mu. And so this then tells us that a prime mu is equal to u a mu u inverse minus d mu u inverse. Okay. So the point is you have local gauge invariance if the gauge field matrix defined as this whole thing under a gauge transformation transforms this way. And so this is the magic that Yang and Mills discovered now, God, 70 years ago, was it? It was in the mid-50s somewhere. Oh shit, I just spilled the water. No, that would be on PBS. Okay, so that's just a review there of non-abelian gauge theory. Now, let me skip the part involving Dirac brackets, which, if you want, look in Weinberg, volume 2, chapter 1 or 2, pages 14 to 18. And what he shows is that then the time-ordered product of some operators, and we're thinking here of gauge invariant operators, is a ratio of path integrals. So this is the thing that we've seen many times. E to the I, the action, a gauge fixing condition, and as an example, we can say that the z component of each gauge field is 0 at every point in space-time. And then we can say ZA d psi. Well, there we're saying d psi bar d psi. So, but I'm going to just write that as d psi. So this is too much trouble to write everything in detail. So this is then e to the I as gauge fixing condition, and okay. All right, so that's our that's analogous to what we had in quantum electrodynamics, And okay, let's take that as a starting point. And this functional delta function, let me maybe make it more explicit. Delta, yeah, I wrote it, yeah, these square brackets means that it's a functional delta function. So dA3 then is a product over all space and over all B of delta. Well, that's odd. That's a typo right there. So let's make that an A. So it's an infinite product of delta. Anybody? Here. So, this is our starting point. Now, physicists initially had real problems computing scattering amplitudes in non-abelian gauge theory. The first person to show how to do this to second order was Bryce DeWitt, who was at the University of Texas at Austin, and wrote very careful papers, long papers on non-abelian gauge theory and quantum gravity using traditional canonical quantization, no path integrals. Just, he might have had some, but basically he was doing traditional quantization and probably using Dirac brackets and so forth. And he managed, well, I'm sure he used Dirac brackets. And he managed to show how to do second order, how to do Feynman diagrams to one loop in non-abelian gauge theory. And his papers were very long and, of course, hard to read. Well, not hard to read because he wrote poorly, but hard to read just because he was doing something that's very hard to do. And in fact, Feynman himself didn't, I don't know whether he was able to do it or not, but I think maybe Bryce DeWitt was the first. Okay. Then, the same year, two Russians, Faddeev and Popov, showed how to do it using path integrals. And their path integral paper, I think, was probably not more than 4 pages. And unfortunately, I think it was published in Physical Letters, which means it's probably now totally inaccessible. Probably has 4 typos because people at Elsevier don't give a shit about science. Okay, so let me try to show you what the Faddeev-Popov trick was. Well, first of all, we saw here, this is a general gauge transformation. If we say that U is, let us say, e to the I, maybe lambda ATA, where the lambdas are infinitesimal and depend upon space-time. So something like this, and it may be that I need a minus sign. This is the infinitesimal form of the gauge transformation. A prime, which I'll write as A lambda of A sub A mu, is A mu, leading term, minus D mu lambda A. So that's just the kind of the gauge transformation of abelian gauge theory. And then minus G F ABC A B mu lambda C. So at the lowest order for infinitesimal lambda, this is the infinitesimal gauge transformation. Now, what we're going to do is compute the Jacobian of this. How does this depend upon lambda? And so the Jacobian we're going to define as, well, it always is the determinant. But now, because this is you know, we're thinking of this matrix as a matrix in which the rows are, or the columns, I don't know, let's say the columns are the points x of space-time, and the rows, maybe those are the rows. Anyway, the columns then are the points y of space-time, one way or the other. This then is a, instead of just an ordinary derivative, it's a functional derivative. And we're thinking of g here is the gauge fixing term. So here the gauge fixing term was was delta of A3. I'm just going to call that G, GB of X. Well, A, sorry. That determinant at lambda equal to 0. So this is, I'm going to call that J. And I'm going to write that as dg lambda, d lambda, lambda equals 0. Capital D just means that it's a functional grid, functional Jacobian. And
What's capital G? I'm sorry.
what's capital G? All right, let me give you an example. Capital G, so A of X might be d mu A mu A of X. Or, in fact, 1/2 of that, no, that's right. Or another possibility is G of A of X is just A3 of X. It's whatever we're going to set equal to 0.
Okay.
So let me get you a candy for your question. Okay. So G is the gauge fixing condition, and we're going to be thinking of many different gauge fixing conditions. And B of G is the delta function that enforces this condition. So this is product, for example, over X and A. Delta of GA of X. And as an example, this might be product over X and A, delta of AA3 of X. In an axial gauge. Another possibility is B of G. And now, when the delta, the gauge fixing functional B isn't always a product of delta functions. In fact, one can think of this: e to the I over 2 integral G of A of X squared d4 of X. And so, in particular, when this is the Lorentz condition. So, by the way, in the lingo this is the axial gauge, this is the Lorentz gauge condition, I should have said. So this would be E, and for some reason we put in a minus sign. Minus I over 2 integral d mu A of X squared. All right, so what we want to do is we want to understand functional integrals that look like this: vacuum time order product O1 O n equals the ratio of function intervals O1, ON, e to the I. S, by S we mean this thing, this line up here. And then we have here B of G, J, dA d psi, and psi of course stands for psi inside bar. And we divide, of course, by e to the I S B of G J dA. Okay, so that's our
There's also
that's the sort of thing that we want to understand, and we want to be able to eventually turn this into Feynman diagrams. Correct. And now the point is that this is a generalization of what we started with, and the generalization is the following: that we, of course, picked B of G to be this, and the difference is that we have a Jacobian here. But the Jacobian of this particular case, where it's, that Jacobian is what? Well, it's a Jacobian of the way in which this changes with respect to lambda. And the change of that turns out to be a constant that cancels. I didn't look at this recently, but basically in this case, this J is a determinant of delta AB, the Z derivative of delta of x minus y. So that's something puzzling, something singular, but it's ultimately a number. And since it occurs in both places, it cancels, so we don't worry about it. What I'm a little puzzled about is why it is that doesn't involve A at all, but presumably it doesn't. And, so let's just, as I said, I didn't check that recently, but it's something that cancels. So we want to understand basically this. And now we're going to use that same trick that we did before, namely we think about shifting by a gauge transformation. And we can shift, if we shift the numerator it doesn't change, so we can shift one way in the numerator, a different way in the denominator. And what happens? Well, we would get, these guys would change by lambda. We would get BG of lambda, J lambda, A lambda, psi lambda, and this one could be lambda prime, lambda prime, lambda prime, lambda prime, lambda prime. Okay. Now here's where we have to insist that the operators be gauge invariant. If the operators are gauge invariant, then we can erase these guys. All right. Moreover, the action, well, the whole point of this is that the action is gauge invariant. So there's certainly no reason to keep these terms. So they go away. And let us take for granted, and or sweep under the rug, the hypothesis that this differential here is gauge invariant, so that goes. For many theories, most theories it is. So that's what we're left with. We're left with some gauge dependence there in the gauge fixing condition and the Jacobian of the gauge fixing condition. And well, that's to be expected, that that's where it would be. But now what we can do is we can integrate, we can multiply by some row of lambda, the same row of lambda, but at lambda prime, and integrate d lambda prime, and we still have the same thing. We haven't really changed anything. Okay, what do we pick? Well, before I say what row is going to be, I skipped ahead a bit here. Let's figure out what J lambda is. Well, J lambda, this is the determinant of the partial derivative of G, A. So we're thinking of two gauge transformations. Because it's G, it's not G, it's G of lambda, and the gauge transformation, remember, is the change in G when you change lambda. So now we want to know what's the change in lambda, in G lambda when you change lambda. And so this is what we're computing, and we can think of this as determinant integral variational derivative of G of lambda x variation lambda c of z variation lambda c of z variation lambda b of y. And of course, whoops, I left out something. And we're doing this all at little lambda equals to 0. Well, this is a product of matrices. The matrix now is a matrix with rows and columns of space-time times the discrete index, the N-goes index. This is a mind-blowing thing. But the determinant of a product is a product of determinants. So this is determinant lambda ax lambda c lambda equals 0, determinant lambda c of z variation lambda b of y, again lambda equals 0. And now, well, if we're setting, if we're going to the lambda equals 0 limit here, we've got just the same thing in both places, so we can just say that this is determinant G of lambda A x lambda c of z lambda equals 0. Whoops, that's big lambda, sorry, that's big lambda. In other words, here we're just letting, it looks like this, we let lambda go to 0 in both cases, and so we just have that. All right, this one here then is determinant of this variational derivative and now we're going to abbreviate these for notation. We're going to call this dg lambda, d lambda, and this thing is going to be d lambda lambda. Little lambda is already 0. This one has little lambda equal to 0. Okay. So in other words, over here, we imagine replacing J lambda and J lambda prime in this way. So let me get another piece of chalk, and this soft chalk makes a good image, but it keeps breaking because it's soft. All right. I'm sort of running out of blackboard space, so let me see if I can fix this right here. Well, we're going to pick, first of all, let's rewrite J lambda, I mean. So let me do the J lambda. Well, the J lambda is going to be d G lambda d lambda, d lambda lambda d lambda, and this at lambda equal to 0. And this will be the same thing here. It'll be d G lambda prime, d lambda prime, and then d, well, I'm going to have to make space, d lambda prime lambda, d lambda prime, maybe I should have another lambda prime, but I'll just leave it like that since we're setting lambda equal to 0 anyway. Okay, now what are we going to choose as this row? Well, what we're going to choose as row is we're going to say that row of lambda is d lambda lambda d lambda lambda equals 0 inverse. Nifty choice, because then row of lambda cancels this thing. Okay. So with that choice of row, we get rid of this, we get rid of that. We've gotten rid of that and that. Okay. So now that's what we've got. But now you see, if you have this thing, dg lambda, dg lambda, d lambda, d lambda, well, that just turns into dg lambda. Lambda, not A. And this thing also turns into dg lambda prime. And cancel the d lambda prime. So this is what we've got now. And so now, we just do this integral dg, we integrate now over all gauge transformations. It's funny, I already canceled that. Well, let me tell you what I want to have. I want to have integral O1, On, e to the is, dA, d psi over integral e to the is, dA, d psi. And I guess the point is we just integrate over dg. Okay. we integrate over dg, and we have whatever the integral of dg of b of g is, cancels both sides, and so that's gone, and we have this. All right, so this is a very, very nice result, and it's in fact, it's probably pointing at something beyond ordinary physics. I don't know why, but notice what's happened. We have the mean value of gauge, of time order product of gauge invariant operators in the ground state. Well, I've got to use one notation or the other. It's the gauge invariant operator is e to the I, the fully gauge invariant action, integrate over all the fields. So in other words, it's just Feynman's original recipe taken as a ratio, and you just integrate over everything. And the fact that this is what's right, and you either get it by these Faddeev-Popov tricks, or you get it to the second order by canonical quantization and just a sort of masochistic intellectual exercise. And that they both lead to the same thing, sort of suggests that there's maybe some principle of physics that points directly at ratios of path integrals for some reason other than canonical quantization. Because the route from canonical quantization is so tortured. Because the route from path from canonical quantization together with the Faddeev-Popov, well, that's much faster, but it is a bit of a skydive intellectually. This is probably something, if we understood physics better, there would probably be a more direct way of getting at that result, I would hope. Okay, there's an analogous formula in Euclidean space, and let me write that down. Now this is the ground state, time-ordered product, gauge invariant operators again, but now they're Euclidean time order. So maybe I should say Euclidean time order. And what is this? This is O1, On, e to the minus Euclidean action, dA, d psi, over integral e to the minus Euclidean action, dA, d psi. Okay, now this, this is essentially the basis of lattice gauge theory or lattice field theory. And, I'll just say that. Okay, we have a few minutes left. Yes?
Just math questions, and I'm good. Two's
well,
enough.
I need to get a chalk anyway.
Okay, two's enough. So the interval dz within the determinant.
I'm sorry, which?
Just two questions on the J lambda. So you have a determinant with the, when you're integrating those two matrices.
Where are we?
First line?
Up here.
Correct.
Here.
One more term? One more.
Over to here.
Yeah, so you have the determinant of the integration of two matrices.
Right.
What happened?
So we're summing over C and integrating over Z.
So what happened to the integration when we went from the determinant of a product to the determinant of two product of two matrices?
Well, in other words, in this particular case, the row index is CZ.
Okay.
The column index is BY.
Okay.
For this matrix. For this matrix, the row index is, I guess, AX, and the column index is CZ.
Okay.
And you have that, and then you sum over the, the adjacent indices, C and Z. Sum over C, integrate over Z. And so that is the determinant of a product of matrices, and that therefore is the product of the determinants.
and then we set lambda to 0 in the
In
next
this one.
line.
Yeah,
Why not in the second term? Why doesn't it go to 0 in the second term?
well, we do set it equal to 0, but we first have to do the functional derivative before we set it equal to 0.
Okay.
Good questions. Okay, it's too bad it's not late October because the subject of the next topic is ghosts. And so the question is, how do we in other words, here we got to an expression for our time-ordered products in terms of ratios of path integrals, integrate over all the gauges. Okay. On the other hand, if we want to do perturbation theory, we don't want to integrate over all the gauges. We want to fix the gauge. And in fact, we want to fix the gauge covariantly, so we want to use this kind of a gauge fixing condition. Okay. So we go back to the earlier expression. In other words, we go back to the expression we had before we had this, which is to say no integration over d of g. It was just, we go back to that expression, s b of g. Oh, we need a j though. dA side. So that was our earlier expression. We go to there. And now we choose b of g. So now we're saying omega t, and now we're in real space-time. B of g See, the part that people were missing was they knew it had to be something like O e to the is b of g, and they could get away with what b of g was if they used the axial gauge, because the Jacobian was simple and it canceled. But they didn't know that they had to have a Jacobian until Faddeev-Popov pointed that out. Okay, so now what we're saying is b of g is e to the I over 2 integral ga of x squared d4 of x, and for some reason I rewrite that as e to the minus I over 2. I don't know whether this was a mistake or what, but I mean, there's nothing inconsistent about it. It's just G has an extra I in it. But anyway, this is the way my notes read, so I suppose there was some reason for that. Okay, well, so this is our B of G. Well, what does that mean? That means that this expression here is integral O1 ON e to the is minus I over 2, well, minus I over 2, so it's minus I over 2 integral d mu a mu squared d4 x, and then the rest of it is j dA d psi. And then we divide by integral e to the I, and let me just call this S prime j dA d psi, where S prime is S plus this gauge fixing term. Well, as you remember, this is, and this, let us put an A there. But this is a very much an abelian gauge fixing term. It's just this, it has a trivial dependence upon A. For each, let us say it's SU3, well, there are 8 A's in SU3, because there are 8 generators of SU3. So we have 8 values of A, and we just put in d mu, A mu A squared 8 times. And then so it's like 8 copies of the gauge fixing term for QED. And so this just gives us, for each of the 8 gauge fields, it gives us a simple propagator. And so this means then that the time-ordered product of AA mu of X, AB nu of Y is minus delta AB delta mu nu of X minus Y. And that's just minus I integral of eta mu nu delta AB q squared minus I epsilon e to the I q x minus y d4 q over 2 pi to the 4th. So using this gauge fixing term, we get simple propagators we get Lorentz gauge propagators, just as we did with in the QED case. However, we still got the J, and that was the Faddeev-Popov contribution, namely that we use the BG to get nice propagators, but we have to compute J. And what's J? Well, I wrote down what A lambda was. It's that formula in the lower left corner there. You see the formula in the lower left. Well, I could go down here and just underline it. So this is how the gauge, this is the gauge transformation of infinitesimal lambda. And now we have to compute the Jacobian, which is, well, it's right over here. It's the derivative of the gauge fixing term. The gauge fixing term is this. So it's the derivative of d mu a mu lambda with respect to lambda. And so we have to compute what g lambda is, g little lambda. G little lambda a of x is then I d mu a mu of x plus I d mu. The d mu comes from the Lorentz gauge condition. And now integral minus delta AC d mu minus g f ABC AB mu of x delta 4 of x minus y lambda c of y d4 of y. So I'm writing this how the Lorentz gauge condition looks in terms of the lambda of this general lambda, so I can do the functional derivative. And then the functional derivative is, we're sort of running out of time here, dg lambda a of x d lambda c of y at lambda equal to 0 is minus I delta AC box delta 4 x minus y minus IG structure constants FABC, and now d by dx mu of a mu b of x delta 4 x minus y there. So that's that, and now what we need is we need the determinant of that. So J is just determinant of ditto. Okay. Well, you might say that's hopeless. How are you going to compute the determinant of something that's this singular and complicated? Well, the Grassmann variables come to our rescue. Namely, that what we learned a long time ago is, in fact, it's this identity, but with zeta equal to 0. And this identity tells us that the determinant of some funny matrix is just e of the Grassmann integral of e to the minus theta dagger a theta. So that's not so bad, because all we have to do is take this structure here, multiply by some Grassmann variables, put it in the exponential, and we just have a more complicated action. Well, I think I should do that for you again next time. So I'll pick up more or less here on Thursday. And okay, are there any questions before we stop? No. All right, I guess we can turn the camera.